Welcome! In this video, we'll tackle LeetCode problem number 2040, kth smallest product of two sorted arrays. This is a fascinating problem that challenges us to compute the kth smallest product from two sorted arrays. We'll explore different approaches and break down the solution step by step. Let's dive right in. In this problem, we are tasked with finding the kth smallest product from two given sorted integer arrays, nums1 and nums2. A product here is defined as the multiplication of any element from nums1 with any element from nums2. The goal is to return the kth smallest product when all possible products are sorted in non-decreasing order. The input includes the two sorted arrays and the integer k, which indicates the position of the product we are looking for based on a 1-based index. The output is a single integer representing the kth smallest product. For example, if nums1 is 2, 5, nums2 is 3, 4, and k is 2, we need to determine which product is the second smallest among all possible combinations of elements from these two arrays. The output for the first example is 8. Let's break this down. The products of all possible pairs from the arrays nums1 equals 2, 5, and nums2 equals 3, 4 are calculated as follows: 2 asterisk 3 equals 6, 2 asterisk 4 equals 8, 5 asterisk 3 equals 15, and 5 asterisk 4 equals 20. When we sort these products in non-decreasing order, we get 6, 8, 15, 20. Here, the second smallest product is 8, which matches our desired value of k equals 2. This demonstrates how the problem asks us to determine the kth smallest product efficiently. In the second example, the input arrays are nums1 equals -4, -2, 0, 3, and nums2 equals -2, -1, 1, 2, with k equals 6. The output is 0. To explain, we calculate all possible products by multiplying each element of nums1 with each element of nums2. Some of these products include -4 asterisk -2 equals 8, -4 asterisk -1 equals 4, -4 asterisk 1 equals -4, and -4 asterisk 2 equals -8. Moving to the next element of nums1, we calculate -2 asterisk -2 equals 4, -2 asterisk -1 equals 2, -2 asterisk 1 equals -2, and so on. We also account for products involving 0, such as 0 asterisk -2 equals 0 and 0 asterisk 1 equals 0. Finally, we include products involving 3, such as 3 asterisk -2 equals -6 and 3 asterisk -1 equals -3. With all these calculations, we build the complete list of products. Continuing from the products, we also have 3 asterisk 1 equals 3 and 3 asterisk 2 equals 6. When we sort all these products in non-decreasing order, the list becomes -8, -6, -4, -4, -3, -2, 0, 0, 0, 0, 2, 3, 4, 4, 6, 8. The sixth smallest product in this sorted list is 0, which matches the given output. This example highlights the importance of correctly sorting the products and efficiently identifying the kth element, especially when the arrays include negative numbers and 0. In the third example, the input consists of nums1 equals 1, 7, 10, nums2 equals 2, 3, 6, 8, and k equals 10. The output is 30. Here, we compute all possible products of pairs from the two arrays, sort them, and identify the 10th smallest product. While the explanation doesn't detail each individual product, the process remains the same: calculate all combinations, sort them, and access the kth product in the sorted list. This example illustrates how the approach scales to larger arrays and higher values of k. The problem comes with several constraints and edge cases that we need to consider. First, the arrays can be large, with lengths up to 100,000, and their elements can range from -100,000 to 100,000. This means the total number of products could reach 10 billion in the worst case, making a brute force solution infeasible. Edge cases include scenarios where all elements are negative, which would produce positive products, or when arrays contain 0, or some products may be 0. Additionally, handling large values of k efficiently is critical, as well as managing cases where one array has only a single element. To solve this problem within these constraints, we need efficient strategies like binary search combined with a counting function to avoid directly computing and sorting all products. This approach allows us to meet the problem's requirements while staying within acceptable performance limits. To begin, let's look at the brute force approach, which is the most straightforward way to tackle this problem. The idea is simple: compute the product of every possible pair of elements from the two arrays, store these products in a list, sort the list, and then return the kth smallest product. While this method is intuitive and easy to implement, it comes with significant computational costs. Specifically, the time complexity is dominated by the product generation and sorting steps, making it m*n plus p*log p, where m and n are the lengths of the two arrays, and p is the total number of products generated, which is m*n. Additionally, this approach requires m*n space to store all the products. The trade-off here is clear: while the method is simple, it quickly becomes infeasible for large input sizes due to its quadratic growth in both time and space complexity. Now, a more efficient strategy involves using binary search directly on the product values rather than generating all possible products. The key observation here is that we can count how many products are less than or equal to a given value, leveraging the fact that both arrays are sorted. This allows us to determine whether the kth smallest product lies above or below a certain threshold without explicitly computing all the products. We start by defining a search range, bounded by the smallest and largest possible products, and use binary search within this range. For a midpoint value, we calculate the count of products less than or equal to it using a two-pointer technique, which runs in m plus n time. Depending on whether this count is less than or greater than k, we adjust the search range. This approach is highly efficient, with a time complexity of m plus n *log max_product min_product, and it requires only 1 additional space. However, it does require careful handling of edge cases, especially when negative numbers are involved, as they can affect the product ordering. Despite being more complex to implement, this method is significantly faster and more scalable than brute force for larger input sizes. Another interesting method is the priority queue or heap-based approach, which dynamically tracks the smallest products. Here, we initialize a min heap with the products of the first column, that is, the product of each element in the first array with the first element of the second array. From there, we repeatedly extract the smallest product from the heap, adding the next product in the corresponding row to maintain the heap size. This process is repeated k times until the kth smallest product is found. The time complexity for this approach is k*log min n due to the heap operations, and the space complexity is min n for storing the heap. While this method is efficient for smaller values of k, its performance can degrade as k increases, given that we need to perform more heap operations. Additionally, the heap can grow significantly if the input sizes are large, leading to higher memory usage. Overall, this approach strikes a good balance for certain scenarios but may not be the best choice when scalability is a concern. Among the three methods discussed, the binary search approach stands out as the most efficient and scalable for solving this problem. It avoids the overhead of explicitly generating all products, as required by the brute force method, and it scales better than the heap-based approach for larger values of k. The key insight here is the ability to count products less than or equal to a target value efficiently, which allows us to narrow down the search range for the kth smallest product without directly working with all possible products. However, this approach does come with its own challenges, such as handling edge cases involving negative numbers and ensuring accurate implementation of the counting logic. Despite these complexities, the binary search method provides the best balance between efficiency and scalability, making it the optimal choice for competitive programming and large input sizes. By leveraging the sorted nature of the arrays, we achieve a solution that is both elegant and highly performant for this problem. To solve this problem, our goal is to find the kth smallest product that can be formed by multiplying elements from two sorted arrays, nums1 and nums2. Since the arrays are sorted in non-decreasing order, we need to carefully account for edge cases such as negative numbers, zeros, and large input sizes. Let's first consider a straightforward brute force approach. The first step is to generate all pairwise products by iterating through each element in nums1 and multiplying it with each element in nums2. For example, if nums1 is 1, 2, and nums2 is 3, 4, the products would be 1 by 3, 1 by 4, 2 by 3, 2 by 4, which simplifies to 3, 4, 6, 8. Next, we sort this list of products in ascending order, which ensures that we can directly access the kth smallest product by using its index. Sorting a list of size m*n, where m is the length of nums1 and n is the length of nums2, has a time complexity of O, m*n*log, m*n. Finally, we return the product at index k1, since array indices are zero-based. While this approach is simple and intuitive, it becomes computationally expensive for large input sizes, as we'll see next. Let's walk through an example to illustrate this brute force approach. Suppose our input arrays are nums1 equals 1, 2, and nums2 equals 3, 4, and k equals 3. First, we generate all the products 1 by 3, 1 by 4, 2 by 3, 2 by 4, which results in 3, 4, 6, 8. We then sort this list, which in this case is already sorted as 3, 4, 6, 8. To find the kth smallest product, we access the product at index 2, which is 6. So the third smallest product is 6. Now, let's explore some key insights. The first is handling negative numbers. Since both arrays are sorted, negative numbers often appear at the start. Multiplying two negatives yields a positive result, so we need to ensure proper handling of all pairings to maintain the correct order of products. For example, if nums1 is -2, -1, 0, 1, and nums2 is -3, 4, we must carefully pair elements to ensure the products are ordered as expected. The second insight is the inefficiency of this brute force approach. When nums1 and nums2 are large, say with lengths near 10 to the power of 4, the total number of products can exceed 10 to the power of 8. This makes the brute force approach too slow and memory intensive for practical use, motivating us to consider alternative methods. The brute force approach relies heavily on data structures and operations that can quickly become inefficient for large inputs. Specifically, we use a list to store all pairwise products. While simple to implement, this approach has significant memory overhead when the arrays are large. Let's analyze the key operations and their complexities. First, generating all products requires two nested loops, resulting in a time complexity of O, m*n, where m is the length of nums1 and n is the length of nums2. Next, sorting the products list, which has a size of m*n, takes O, m*n*log, m*n. Finally, accessing the kth smallest product in the sorted list is a constant time operation, O1. When combined, the overall time complexity of this approach is O, m*n*log, m*n. This is computationally expensive for large arrays, as the number of products grows exponentially with the lengths of nums1 and nums2. Therefore, while the brute force method is conceptually straightforward, it is not scalable, and we need to explore more efficient solutions. To address the inefficiencies of the brute force approach, we can use more optimized techniques that reduce both time and space complexity. One such optimization is the binary search approach. Instead of generating all products explicitly, we can use binary search to directly determine the kth smallest product. This avoids the need to store all products in memory, significantly reducing overhead. Another powerful technique is the two-pointer approach, which leverages the sorted nature of the arrays. By strategically selecting pairs of elements, we can efficiently locate the kth smallest product without explicitly generating every possible pair. These optimizations are particularly useful for handling large input sizes. Finally, we must consider several important edge cases. For instance, arrays containing zeros require special handling, as products involving 0 result in 0, and this must be correctly positioned in the sorted order. Similarly, the multiplication of negative and positive numbers must be carefully managed to ensure the correct ordering of products. For very large arrays, memory optimization becomes critical. Lastly, we need to ensure that the value of k is within the valid range of possible products, which is from 1 to the total number of pairs, m*n. With these considerations, we can create a solution that is both efficient and robust for all edge cases. Here, we define the function kth smallest product within the solution class. The goal of this function is to find the kth smallest product of two numbers, one from each of two sorted arrays, nums1 and nums2. To achieve this, we first define a helper function count_less_equal x that calculates how many products are less than or equal to a given value x. The logic for this depends on whether the current number from nums1 is positive, negative, or 0. For positive numbers, we perform a binary search on nums2 to find the maximum index where the product with the current number is still less than or equal to x. Similarly, for negative numbers, we adjust the binary search to find the minimum index where the product exceeds x, and use that to calculate the count. If the number is 0, all products will be 0, so we simply add the length of nums2 if x is non-negative. This helper function allows us to efficiently count the number of products that meet the condition for any given value of x. The count_less_equal function is then used within a binary search framework to find the kth smallest product. We first initialize the search boundaries, left and right, to cover the entire range of possible products, which could extend from -10 to the power of 10 to 10 to the power of 10. While left is less than right, we calculate the midpoint mid and determine how many products are less than or equal to mid using the count_less_equal function. If this count is less than k, it means the kth smallest product must be larger, so we adjust left to mid plus 1. Otherwise, we narrow the range by setting right to mid. Once the search converges, the value of left represents the kth smallest product, which is returned as the result. This efficient use of binary search ensures that we solve the problem within logarithmic time relative to the range of possible products. Here, we begin our Java implementation by defining the class and the method kth smallest product. The goal of this method is to find the kth smallest product between two sorted arrays, nums1 and nums2. We start by defining two boundaries, left and right, which represent the possible range of products. Since the product can be as low as -10 trillion and as high as 10 trillion, these bounds are set accordingly. Next, we use a binary search approach to narrow down the range. The midpoint, mid, is calculated, and we use a helper method, count_less_equal, to determine the number of products that are less than or equal to mid. If this count is smaller than k, it means the kth smallest product must be in the upper half, so we adjust left. Otherwise, we adjust right. Once the binary search converges, the value of left will represent the kth smallest product. The helper method count_less_equal is defined immediately after, and its purpose is to count how many products are less than or equal to a given value x. Let's look at its implementation next. The count_less_equal method is designed to calculate the total number of products from all pairs of elements in nums1 and nums2 that are less than or equal to a given value x. The method iterates through each number in nums1. If the current number is positive, we use binary search on nums2 to find the largest index where the product of the two numbers is still less than or equal to x. The count is then updated by adding the number of valid pairs. If the current number in nums1 is negative, the process is similar, but the logic for updating the bounds of the binary search is reversed because the product decreases as we move along nums2. Finally, if the number is 0, any product involving it will also be 0, so we simply add all elements of nums2 to the count if x is non-negative. This ensures that all cases, positive, negative, and 0, are handled correctly, and the method returns the total count of products less than or equal to x. With the implementation complete, the solution class provides a robust method for solving the problem of finding the kth smallest product. The count_less_equal helper method works seamlessly with the binary search and kth smallest product to efficiently narrow down the range of possible results. This approach ensures that the solution is both time efficient and handles edge cases like negative numbers and zeros effectively. Overall, the combination of binary search on the product range and careful counting within count_less_equal allows us to tackle this challenging problem with precision. To solve this problem, we need to find the third smallest product from two sorted arrays, nums1 and nums2. First, we set up binary search boundaries by initializing left to -10 to the power of 10 and right to 10 to the power of 10. These boundaries represent the range of potential products we are considering. With binary search, we calculate the middle value, mid, as the average of left and right. Initially, mid is 0 because left is -10 to the power of 10 and right is 10 to the power of 10. Next, we use a helper function called count_less_equal to determine how many products are less than or equal to mid. For each number in nums1, we check how many products we can form with elements in nums2 that are less than or equal to mid. For number 1 equal to 1, binary search on nums2 gives 0 products less than or equal to 0. Similarly, for number 1 equal to 2, there are also 0 products less than or equal to 0. This makes the total count of products less than or equal to mid equal to 0. Since this count is less than k, we adjust our binary search range by setting left to mid plus 1, which is now 1. We then calculate a new mid value, which becomes 5 billion based on the updated range. With the updated mid value of 5 billion, we again count how many products are less than or equal to mid. For number 1 equal to 1, binary search on nums2 shows that all two elements in nums2 yield products less than or equal to 5 billion. Similarly, for number 1 equal to 2, both elements in nums2 also produce products less than or equal to 5 billion. This gives a total count of 4 products less than or equal to mid. Since this count is greater than or equal to k, we refine our search range by updating right to mid, setting it to 5 billion. We continue narrowing the range by recalculating left and right through repeated binary search. This process continues until left equals right. At that point, the value of left represents the third smallest product, which is 6. Now, let's consider a second example where nums1 is -2, -1, nums2 is 1, 2, 3, and k is 4. As before, we initialize the binary search boundaries with left set to -10 to the power of 10, right set to 10 to the power of 10, and mid calculated as the average, which starts at 0. Using the count_less_equal function, we count how many products are less than or equal to mid. For number 1 equal to -2, binary search on nums2 shows that 2 products are less than or equal to 0. Similarly, for number 1 equal to -1, there are also 2 products less than or equal to 0. This gives a total count of 4 products less than or equal to mid. Since this count is equal to k, we adjust our search range by setting right to mid, updating it to 0. We continue to narrow the range, adjusting left and right iteratively. When the two boundaries converge, the result is -2, which is the fourth smallest product. In the final example, nums1 is 0, 1, 2, nums2 is -3, -2, -1, and k is 5. We start by initializing left to -10 to the power of 10, right to 10 to the power of 10, and mid to 0. Using the count_less_equal function, we calculate how many products are less than or equal to mid. For number 1 equal to 0, all products are 0, which results in 3 products less than or equal to 0. For number 1 equal to 1 and 2, binary search shows no products less than or equal to 0. This gives a total count of 3. Since this count is less than k, we adjust the range by setting left to mid plus 1, updating it to 1. We continue applying binary search, narrowing the range further. When left and right converge, the result is -2, which represents the fifth smallest product. This example highlights how binary search efficiently reduces the range of possible products, leveraging the monotonicity of product counts. The count_less_equal function ensures that we can quickly determine the count for any given mid, resulting in an overall time complexity of O, m plus n, *log, max_product. To analyze the time complexity, we start by understanding the two major components of the solution, the binary search on the product range and the helper function count_less_equal. First, the binary search is performed over the possible range of products, which is from -10 to 10, a range determined by the constraints of the problem. The number of steps in binary search is proportional to the logarithm of this range, which simplifies to O log 2*10 to the power of 10, or equivalently O 30, since the range size is constant. Next, we have the count_less_equal x function. For a given midpoint during binary search, this function calculates how many products are less than or equal to x. It iterates through each element in nums1 and performs a binary search on nums2 to find matching pairs. Since iterating through nums1 takes m steps, and each binary search on nums2 takes O log n, the total complexity of this function becomes O m *log n. Now, combining the two components, the binary search on the product range invokes count_less_equal x at each of its steps. This means the overall time complexity is the product of the binary search complexity and the complexity of count_less_equal x. Substituting the values, we get O log range *count_less_equal, or, more specifically, O 30 m *log n. Since 30 is a constant, the final time complexity simplifies to O m *log n. For space complexity, the binary search itself only uses a constant amount of space for variables like left, right, and mid, making its space usage O1. Similarly, the count_less_equal x function does not require additional memory beyond a few counters and loop variables, which are also constant in size. Therefore, the total space complexity of the optimized solution is 1. When comparing the optimized solution to a brute force approach, the differences in efficiency become clear. A naive solution would compute the Cartesian product of the two arrays, which involves pairing every element of nums1 with every element of nums2. This operation takes m*n time. After generating the Cartesian product, we would need to sort the resulting array of products, which has a time complexity of m*n*log m*n. This results in an overall time complexity of m*n*log m*n for the brute force method. Additionally, the brute force approach requires m*n space to store the Cartesian product. In contrast, the binary search solution avoids explicitly generating all products by leveraging the sorted nature of the arrays and narrowing the range efficiently through binary search. This reduces the time complexity to m*log n, which is significantly faster for larger arrays. Furthermore, the optimized approach only requires 1 space, making it far more space efficient than the brute force method. Finally, let's analyze the best and worst case scenarios for the optimized solution. In the best case, the binary search converges quickly to the answer, such as when k is small. However, since the count_less_equal x function must still process all elements of nums1, the overall time complexity remains m*log n. In the worst case, the binary search executes all its 30 iterations, calling count_less_equal x at each step. Even then, the time complexity remains m*log n, as this represents the general case. To justify this mathematically, binary search reduces the search space by half during each iteration, leading to log range iterations. Within each iteration, the count_less_equal x function performs binary search over nums2 for each element of nums1, resulting in m*log n. Combining these two steps gives the final complexity of log range m*log n, which simplifies to m*log n. This analysis highlights the efficiency and scalability of the optimized approach, especially when compared to the brute force method, making it the preferred solution for large datasets. When solving this problem, there are several common mistakes to watch out for. First, handling negative numbers incorrectly can lead to significant issues. Remember, the product of two negative numbers results in a positive value, which can change the ordering of products. You need to carefully consider all combinations negative with negative, positive with positive, and negative with positive to ensure your solution accounts for every scenario. Next, zeros in the arrays can introduce unique edge cases. If 0 is present in either array, it can dominate the smallest product calculation, as any number multiplied by 0 equals 0. Explicitly handling 0 is crucial to avoid errors. Another frequent mistake is relying on brute force solutions. While computing all possible products might seem straightforward, it's computationally expensive, with a time complexity of n squared. Optimized techniques like binary search or two-pointer methods are essential for dealing with larger input sizes. Lastly, misunderstanding the kth smallest product can lead to incorrect results. Remember, kth smallest refers to the position in a sorted order of products, not just the kth index in an unsorted list. Always recheck the problem constraints to ensure your approach aligns with the requirements. Handling large numbers is another critical consideration. When working with products, especially in programming languages like Java or C++, integer overflow can occur if the numbers are large. To prevent this, use data types that can store larger values, such as long in Java, and consider applying modular arithmetic if necessary. Now, let's dive into some key insights for interviews. Binary search is a powerful optimization tool for kth smallest problems. Instead of iterating through all pairs, you can apply binary search on the product values to efficiently narrow down the range. The two-pointer technique is another great strategy when working with sorted arrays, as it allows you to explore pairs systematically while maintaining optimal efficiency. Pre-sorting the arrays is often a helpful step as well, because it simplifies the logic and lets you make assumptions about the relative order of elements. During interviews, it's also important to communicate the trade-offs in your solution. For example, explain why a brute force approach is too slow and how your optimization reduces the overall complexity. Finally, if you want to deepen your understanding of similar problems, you can explore related LeetCode challenges such as kth smallest element in a sorted matrix, find kth smallest pair distance, and merge k-sorted lists. These problems share similar patterns and techniques, making them excellent practice. Now, let's discuss some alternative approaches you can consider. First, binary search on product values is an efficient method, especially for large arrays. Here, you search within the range of possible product values to determine the kth smallest product. This approach has a time complexity of O(n*log max_product, but you'll need to carefully design it to ensure correctness, particularly when handling edge cases. Another option is a heap-based approach. By using a min heap, you can iteratively track the smallest products as you generate them. This method is often easier to implement, but it typically requires more space, so you must manage memory usage carefully on larger datasets. Finally, there's the divide and conquer strategy. This involves breaking the problem into smaller chunks and solving each subproblem recursively. While this approach can be harder to implement, it's particularly useful for scenarios where parallel processing is feasible, allowing you to leverage computational resources efficiently. Each of these methods has its trade-offs, so choosing the right one depends on the specific constraints and requirements of the problem you're solving. Great job! We've explored the problem, understood its intricacies, and walked through efficient solutions step by step. Remember the importance of binary search and leveraging problem constraints. Thank you for watching. Don't forget to like, subscribe, and stay tuned for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!